Thank you. It's much appreciated for me to be invited to this conference. I'm from Virginia, and you can find out more about me at my homepage. Or if you want to find out about any of my papers, I always put them on the archive. So, approximating Betti numbers over arbitrary fields. So, L2 Betti numbers are a fairly well-known concept, and here the ground ring is either the complex numbers or sometimes just the real numbers. So I'm going to look at doing this over arbitrary fields, in other words, fields of non-zero characteristic or even skew fields. This is mainly joint work with Wolfgang Luck, Roman Sau, and Thomas Schick. So the problem could be described as follows. So let G be a skew field, let G be a group, let M be a right KG module, and supposing we have a descending sequence of normal subgroups of finite index in G intersecting in the identity. In other words, G is residually finite, and then you could ask if X is a finite free GCW complex, what can be said about the limit of those dimensions of those homology groups? Well, the sort of homology groups, the dimension normalized, you divide by the order G over Gn. Or if M is a finitely presented KG module, what can be said about the limit as you take takes this quotient of these dimensions here, these are successive quotients of M, you keep modding out by the action of Gn. What can be said about that? Or alternatively, if you have a matrix over Kg, you let AN denote the image of that matrix mod G over G mod Gn, what can be said about the limit as n tends to infinity of the rank of n, or rather, more precisely, sort of the normalized rank you want to divide out by G over Gn. So let me review some stuff. So group von Neumann algebra. So L2 of G, denote the Hilbert space with Hilbert basis, the elements of G. L2G, you can think of them as formal sums, sigma A, G, and G, such that the coefficients are square summable. You know, multiplication, or sometimes you call it convolution. And if you take two elements of L2G, multiply them together, you get something in L infinity of G, in other words, one in which the coefficients are bounded. In general, if you multiply two elements in L2 of G, you'll lie outside L2 of G. So you define the group von Neumann algebra as those elements in L2 of G, such that alpha beta is in L2 of G for all beta in L2 of G. So N of G is a subspace of L2 of G, which is also an algebra. For example, if G is finite, the group von Neumann algebra is just the complex group ring. If G is C, then the group von Neumann algebra is just the measurable functions on the torus, and the operation is pointwise multiplication and addition. And you also have an involution from L2 of G to L2 of G. Take sigma A G G to sigma A bar G inverse, where A bar is the complex conjugate of A. Then a projection N of G is a self-adjoint idempotent. In other words, an element E such that E equals E squared equals E star. So usually energy has uncountably many projections, and in the case of the group von Neumann algebra of C, the projections just correspond to the measurable subsets of T. So you can define von Neumann dimension for N of G modules. So you have a trace defined on N of G, because N of G is, you can think of it just a subset of L2 of G, and so you can take the trace of sigma AGG, just define it to be the coefficient at the identity. And also, if you've given alpha and n of g, there's a unique projection such that alpha n of g is contained in En of g, and in some sense, it's the least such projection. So in other words, if you have another projection, which is a strictly smaller, Fn of g is strictly smaller than En of g, well, then that can't happen if it contains alpha n of g. Then you define the von Neumann dimension n of g of that should say alpha there is a trace of E. Listing the extends to a dimension function, the von Neumann dimension defined on all right n of g modules satisfying the usual properties for a dimension function. So in particular, if you have a short exact sequence, the dimensions will add up. The dimension of the altitude, some of the dimensions of the altitude is the dimension of the middle. The dimension is always a non-negative real number, or it can be infinity. And if you have an ascending sequence of right n of g modules, then the dimension of n of g of the union is the supremum of the dimensions. Of course, it's false if you replace union with intersection and sub with inf there. If g is finite, then you're really just taking the dimension of m over c, but you've got to divide by the order of g. So some review of what Luke did. He proved that if you had the descending sequence of normal subgroups of finite index intersecting in the identity, and if M was a finitely presented QG module, then the dimension n of gm tends to QG n of g. You get it as the limit of taking the normalized dimensions of M modded out by the action of Gn. So he proved it just for the case for the rational numbers, but then this was later extended to the field of all algebraic numbers. Surprisingly, an arbitrary subfield of C, this is an arbitrary group, this is still open whether this remains true. Look also proved if G is an amenable group and M is a CG module, then the von Neumann dimension of Tor NC of Gm n of G is 0 for all positive integers n. So this means that n of G is dimension. You can say it's dimension flat over CG. So actually, it's even for amenable groups, it's rare for n of G to be actually flat over CG. It will certainly be the case if G is finite, but it will be dimension flat. We also want to consider Auray localization. Well, this is to do with forming fields of fractions. Really, we're thinking in terms of the non-commutative case. So let R be a ring and S denote the set of non-zero divisors of R. Then R satisfies the right Auray condition. Means that given R in R and S in S, there exists R1 in R and S1 in S such that RS1 equals SR1. And this is precisely the condition you need to be able to form the Auray ring of fractions Rs to the minus 1, which is a generalization of the classical, non-classical commutative case. And the elements are Rs to the minus 1, and you have the property Rs to the minus 1 equals R1 S to the minus 1. If only if there exists X and R and T and S as Rx equals R1 T and Sx equals S1 T. I say this is just a sort of straightforward but quite complicated generalization of the commutative case. then R S to the minus 1 will be flat over R. And in the case R is a domain that satisfies the right Auray condition, then R S to the minus 1 is a skew field containing R. The class of elementary amenable groups, abbreviated to EA groups, is the smallest class of groups, which includes all finite groups, all abelian groups, and is closed undertaking subgroups, directed unions, and extensions. So they come the sort of, this class is close to being the all solvable, virtually solvable groups, or it's quite close to being the groups which don't contain a non-abelian free subgroup. So anyway, all virtually solvable groups are elementary amenable, and all elementary amenable groups are amenable. And the theorem we want to use is that in the case when G is an elementary amenable group, K is a skew field, S is the non-zero elements of KG, and if G is torsion free, then KG is a right and left Auray domain, and you can form the skew field of fractions KG S to the minus 1. So in the above situation, you can define an Auray dimension on M, namely, you take the dimension over the division ring KG S to the minus 1 of M tensor KG S to the minus 1. If G contains a non-abelian free group, then KG never satisfies the Auray condition. So you can't form this, so you can never form this field of fractions, the skew field of fractions. So there are ways to form fields containing KG, but they won't have such nice properties. They won't be flat over KG. Let's just write LCM for the lowest common multiple of the orders of the finite subgroups of G. If the orders of the finite subgroups of G are bounded, then we say LCM G is infinity. And then you have the following result. If G be an elementary amenable group, in which the finite subgroups of bounded order, and we do need the bounded order there, and let K be a skew field, then there's a subgroup H of finite index, such that if S is a set of non-zero divisors of KH, and the Auray localization KH S to the minus 1 exists, it won't be a skew field, but it'll be quite close. It will just be matrices over a skew field. And then if M is a KG module, one can define the Auray dimension over KG of M as R over D ordered times the order G over H. R is the number of irreducible summons of the MD D module M tensor KH KHS to the minus 1. So this is just an extension of the dimension from the torsion-free case. If G is finite, then this Auray dimension is just the usual dimension over K. Well, you got to, as I say, you got to normalize it. You got to divide by the order of G. So G be an elementary amenable group with the lowest common multiple of the order of G finite. So in other words, there's a bound on the orders of the finite subgroups. Let K be a skew field, then be a finitely presented KG module. Supposing you have a descending sequence of normal subgroups, finite index of G intersecting in the identity, then the dimension, and this always dimension of m, you can get it by taking the limit as n tends to infinity of taking these quotients of m, modding out by the action of gm. So you can combine this sort of these concepts as ultraproducts. Let's K be a skew field and let G be a descending sequence, normal subgroups, a finite index intersecting in the identity. And for a positive integer n, let's define a map, well, the map from K G over Gi to the endomorphism ring of K G over Gi by the left regular representation. And then you set E to be the Cartesian product of these matrix rings. And then these theta i's, they obviously induce a homomorphism Kg to E. That's no problem. But E is a self-injective von Neumann regular ring. It doesn't matter if you don't know what that is. But it's rather sort of like its own infinite matrix ring. But I say it's too big. You want something smaller. So you quotient out this at E's, take a quotient of E. You do it as follows: for positive each positive integer I, let arc rank I subscript I denote the normalized rank function on the nkg over gi. So that will be, so I call that the dimension of the image of alpha divided by the order of g over gi. Then you choose a non-principal ultrafilter on the positive integer. So this is ultrafilter is used for taking limits. So remember what an ultrafilter is on n. It's a collection of subsets of n which is closed under finite intersections, and if anything in that ultrafilter that is bigger than, if you take something in that ultrafilter and it's bigger, then it's still in the ultrafilter. And for any subset of n, either that or its complement, but not both, lie in the ultrafilter. And so the existence of ultrafilters depends on some version of the axiom of choice. So you can't describe them. And so suppose you're given an element of E, let alpha I be its coordinates, then since the rank of alpha I are between 0 and 1, the ultralimit will exist and is well defined, and there will be a number between 0 and 1. In the special case, so it's a bit complicated to describe exactly how lim omega rank A alpha I is, but in the special case, if the rank of alpha I actually converged, then the rank of alpha would just be the limit of that sequence. So in other words, the ultralimit is a way of making sure you always have a limit. And then you set I to be those with this rank 0, then I is an ideal of E, and you'll call U subscript omega kg, define it to be E over I. This will be a simple self-injective von Neumann regular ring, and the rank function also induce a rank function on this von Neumann regular ring. And the map sending beta to theta beta mod I is going to be still an injection. Now, since U omega kg is a simple self-injective von Neumann regular ring, its rank function induces a dimension function on all U omega kg modules, U omega of kg modules, which are called U dim U omega k of kg. And you'll have the following properties: it will always be a non-negative integer or infinity. The dimension of alpha times U omega kg will just be rho of alpha. Then if you have an exact sequence, you have the expected formula. And similarly, if you have an ascending sequence, then the dimension of the union is a supremum of the dimensions of the MI. And it comes from almost the definition that if M is a finitely presented kg module, then dim U omega kgm is the ultra limit of the dimensions of these modules. So let K be a skew field and let G equals G0 contain G1 containing the descending sequence of normal subgroups intersecting the identity such that the quotients are finite. And select a non-principal ultrafilter omega on positive integers. Then if you have an exact sequence of kg modules, then the dimension over U omega of kg, M tensor kg, U omega kg, is the sum of the dimensions of the outer two. And also this dimension will be independent of the GI and the ultrafilter omega. So this means that U omega is dimension flat over kg. So it's model on looks proof that N of G is flat over CG. So of course the G has to be an amenable group here. So we can also look at pro-P groups of finite rank. So if P is a prime and G is a pro-P group, then G has finite rank if there's a positive integer n such that the number of generators of H modded out by the Frattini subgroup of H is at most d for all subgroups H of finite index in G. So the Frattini subgroup here will be commutator subgroup times the p powers of H. I'm also going to want to use later to iterate the Frattini subgroup. So phi I of H is just do phi I times. So let G be a pro-P group of finite rank. So the finite rank means sort of it doesn't get too wide. Then G is so we say G is uniform. I mean, this seems to be quite a weak condition. You say if and only if G over G to the P is abelian, so if you mod out the Pth powers, you get an abelian group. And also the order of G over phi of G is equal to the order of phi I of G, or phi I plus 1 of G. Oh, the only thing is, that should say if P equals 2. That's a bad blunder. So if P is an odd prime, you just take G over G to the P. But if, in the case of an even prime, the even prime in the case of 2, you do actually need G to the fourth here, apparently slightly stronger condition. So examples, so if ZP, the p-adic integers, then the direct sum of the d copies of ZP will have rank D. And another good example are congruent subgroups. In other words, you take groups of matrices which are congruent to the identity modulo P. Then if P is not equal to 2, G1 will actually be a uniform pro-P group, and the Frattini subgroups here, they will just be these congruent subgroups, the matrices mod P to the I for I equals 1, 2, 3, etc. Yes, and if P equals 2, then you can't quite do it with G1, you have to do it with G2. So remark, it's almost terminology. This is G is a topological group, then G is a compact p-adic analytic, or some people use the terminology Lie group if and only if G has a normal subgroup of finite index, which is a pro-P group of finite rank. I should say you count any finite groups as compact p-adic analytic groups. So this is what is a rather strong result due to Prasad. If K is a field of characters P and G is a uniform pro-P group, then you let KG denote the completion of KG with respect to the powers of the augmentation ideal. So in other words, the ideal generated by the elements G minus 1 for G and G. And then KG can be described as the inverse limit of these group rings KG over phi of G, and it will be a Noetherian local ring. And if its maximal ideal is delta, then you can form the associated graded ring, and this associated graded ring happens to be a polynomial ring. So you might want to, just the case when G is, so G could be it could be a congruent subgroup. Matrix is congruent to 1 modulo P. And then if you form this completion and then take this associated graded ring, you finish up with a polynomial ring. And yeah, you can just about do it. It's not too badly. It's just sort of do a Bahn's calculation. So from this you can deduce this result. So if you have a GB uniform pro-P group, and so for alpha n of G, K of G, you let alpha I denote the maps modulo mod GI. And then if alpha is non-zero, then this limit as I tends to infinity, the dimension of the kernel of alpha I divided by the order of G over GI is 0. And really this comes from the fact that this associated graded ring is a polynomial ring. You can sort of reduce the calculation down to looking at polynomial rings to do this. So now, so you can let G be a compact p-adic analytic group and let H be a uniform subgroup of finite index. And by Lazard's theorem, you can form the skew field of fractions KH s to the minus 1, where S is the non-zero elements of KH. And then for finitely presented KG module, you can define dimension KG to 2 square brackets of M. So the dimension of M induced up to K 2 brackets H s to the minus 1, and then divide by G over H. This is independent of the choice of H, and you get that the dimension of K 2 square brackets G of M is the limit of the dimensions of the M tensor kgn k divided by the order of g over gn. And sort of you get a curious result here that this since it's dimensional, will always be a rational number because you're just taking some integer and dividing it by the order of g over h. You've always got this dimension, this limit here is always going to be a rational number. So you want to sort of try and apply this to residually finite p groups in general. So we only have partial theorems on this at the moment. So if P is a prime and K is a field of characters, P let G be a group with a descending sequence of normal subgroups intersecting I. The identity such that the quotients are finite P groups for all I. And supposing the rank of G over Gi is bounded, so remember that means that G over Gi doesn't get too wide. Then you can take the inverse limit, the group of the inverse limit of these G over GIs, and this will be a pro-P group of finite rank, almost by definition. And then you've got the limit as n tends to infinity, dim k, m tends to kgn, k divided by the order of G over GN is equal to this dimension on the right-hand side, and there will always be a rational number. It seems as this depends on the choice of the descending sequence of normal subgroups. It seems to me very plausible it should be independent of the choice of this choice of descending sequence of normal subgroups, but well, that's open at the moment. So relation with the Atiyah conjecture, a G be a group, then U of G will denote the algebra of closed, densely defined unbounded operators affiliated to the group von Neumann algebra of N of G. So that sounds a bit complicated, but so the key properties are that its N of G will satisfy the left and right or a condition. So if and then you get that U of G is just the ring of fractions N of G s to the minus 1. This ring of fractions exists and will be isomorphic to U of G. Of course, it will certainly be very far from being a skew field. If K is a subfield of C, then we'll let dkg UG denote the division closure of kg in U of G. So this is the division closure is going to be the smallest skew field containing kg, and it's contained in U of G. And so such a thing exists because the intersection of two skew fields is clearly a skew field. So just, if you're unfamiliar with this, G is finite, U of G is just isomorphic to C of G. G is C, then U of G will be, I'm not quite sure what the correct letter is. But anyway, it will be isomorphic to the essentially bounded functions on the torus. In other words, those functions such that for any epsilon greater than 0, you can find a big enough number n such that the points where the function is bigger than n has measure less than epsilon. So this allows you to. So this means that in U of G, functions which are non-zero. So in E of T, functions which are non-zero everywhere are invertible, which is not the case with N of G. So one version of the Atiyah conjecture. So if G is a torsion-free group, and K is subfield of C, then dk of G of G is a skew field. I'm really sort of interested in torsion-free groups here, or maybe groups in which the orders of finite subgroups of bounded order. So let Q bar denote the field of all algebraic numbers in C. So, as I said before, Luck's approximation results work for the algebraic integers, but they haven't been shown to work for the complex numbers. And because of this, one can often prove the Atiyah conjecture over the algebraic numbers, but not for the complex numbers. So we have this following result. Supposing, so G to the n denotes the direct product of n copies of G. So supposing the Atiyah conjecture is true for G to the n for all positive integers n. In other words, the division closure of Q bar G and U of G is a skew field. The division closure of Q bar G cross G in U of G cross G is a skew field, and so on. Then the division closure of CG to the nth in U of G to the n is a skew field for all n in n. So I've managed to replace Q bar, managed to get up to the complex numbers. So this means it would be nice if we can sort of improving the Atiyah conjecture, if you can prove not only, if you prove it for group G, it would be nice to prove it for all powers of G, in other words, G cross G, G cross C, cross C, cross G. So we have the following result: if H is normal in G with H isomorphic, well, there's several variations of this. If there's isomorphic to an Artin braid group Bn and G over H is elementary amenable, and if LCM, if the orders are finite subgroups of G, and G satisfies the strong Atiyah conjecture over Cn, over C. And so in particular, if G is torsion free, so I haven't said what it means for this to be true for in cases when G has torsion, but in torsion free case it will mean that the division closure of CG in U of G is a skew field. And you do that by proving Atiyah conjecture over the algebraic integers for all powers of G. I seem to have mistimed this a bit, never mind. So let H normal in G be groups. H isomorphic to an Artin braid group Bn, and G over H elementary amenable, finite subgroups of bounded order. Let M be a finitely presented CG module. Suppose we have a descending sequence of normal subgroups intersecting in the identity. Then the von Neumann dimension of M centered up to n of G is the limit as n tends to infinity of these these normalized dimensions of the quotients. So I'm finished. So in the torsion-free case, any torsion-free subgroups of GLNZ. So for I think 3, yeah, a torsion-free sub, an arbitrary torsion-free subgroup, I think of GL3Z. It's unknown. Yeah, I guess probably if okay, you have finite index, yeah. So, and one sort of would feel one ought to be able to prove it for sort of torsion-free subgroups of things like GLNZ, but the problem is that the pro-finite or pro-P completion of a torsion-free group isn't torsion-free. If it was, then you could quite likely do the problem for arbitrary subgroups of GLNZ, but because these complete, so an interesting case is when these completions have torsion. Oh, and another case, if you take these pro-P groups of finite rank, yeah, it's unknown for it's unknown if say rational numbers or complex numbers. So if you look at torsion-free groups of pro-P groups of finite rank, if you're working over the field with PL, a field of characteristic P, then you sort of know almost everything. But if you go to mixed characteristics, you seem to know almost nothing.
I didn't quite understand. You said that Luke's theorem works for Q but not for C. What is exactly the statement for Q and for C?
So we can see if we can go back. He had it. So here it is. So he's saying that if you take the von Neumann dimension of, one version of it is M tensor kg up to n of g, it's a limit of, so you take m and you mod it out by the action of gn, divide by, so you're taking the normalized dimension, as it were.
So he proved this only when K is Q?
Only when K is Q, that's right. And so it's been extended the case using his arguments, just a small trick on his arguments, get up to algebraic numbers. But the case, if you have any sort of transcendental element, it's not clear how to deal with. Yeah, this is for any group, yeah. This is for an arbitrary group.
You're saying that for Bray groups you can take K to be C.
Yeah, for Bray groups I can take K to be C, yeah, by a rather roundabout argument, but it's sort of proving that the Atiyah conjecture is true for Bray groups. And actually what you do is you use Luke's results, at least for the case when K is the algebraic integers, and use these approximation results to prove it for braid groups if your coefficient ring is the algebraic integers. But actually it shows it's not only true for braid groups but arbitrary finite direct products, and then that will tell you it's true if you work over the complex numbers.